When CO2 is high, dust is low. When CO2 is low, dust is high. And this is why we get this dust production just before every interglacial. It's because of a lack of CO2 causing CO2 deserts, which causes dust, which allows that dust to settle on the northern ice sheet.
I have Ralph Ellis here from the UK.
I'm the original sort of polymath, I suppose. I've been in many industries and with many types of education. So I trained in mineral surveying. Then I became a computer analyst working in London. Then I became a flying instructor. And then I became an airline captain working across on jet airliners across Europe and the world. So I've been studying meteorology for my job for the last 40 years. It's been an essential portion of my job. So that was my background. But back in 2015 or so, I was involved in a lot of these climate discussions, and I was concerned that we didn't actually know how ice ages were controlled. And that seemed a little bit odd to me. It was something to do with orbital cycles, and it must have had a feedback in there as well. And that feedback agent must have been CO2, of course. But this CO2 orbital hypothesis presented many problems that were simply not being explored, addressed, or explained. Certainly not to my satisfaction anyways. And so I set out about discovering a much better solution, and all-encompassing solution. And the result was this peer-reviewed climate paper, which I published in 2016. So that is what I call the best graph, because it was produced by Professor Best. And I think it's rather good. And it has all of the parameters that are involved on the climate cycle for ice ages. So all you need to do is understand what's going on in all of these different elements in this graph, and you'll understand ice ages. And that is what I managed to do in this paper here, which is called Modulation of Ice Ages via Precession and Dust Albedo Feedbacks, by myself, Ralph Ellis, and Professor Michael Palmer. Now, this has been a very successful, influential paper. It's had something like 50,000 downloads, which is quite a lot for a peer-reviewed paper. And it's not really been challenged. So that's interesting. I've had lots of pushback against it and saying, rubbish or whatever, but no one actually trying to systematically falsify what has been said in this paper. So let's have a look at the standard graph that is used in paleoclimate. So this is a graph of temperature in red against CO2 in blue. So along the bottom, we've got dates from 0 on the right. That's today's date, back 800,000 years. So this gives us 10, I think, interglacial periods. So temperature is in red. It's on the left-hand side. So we've got temperatures from -10 to +4 degrees in centigrade, of course. So that's the variation in temperature we get during the ice ages, about 12 or 14 degrees centigrade. Measured at the poles, of course. This is at the high latitudes. During the ice ages, the temperatures at the tropics didn't change very much at all. And that's important. So we'll talk about that later. They only changed by about 2 or 3 degrees in the tropics. And so what do we find here? Well, we have a close correlation between temperature and CO2. And so as we see, as temperature goes up, CO2 goes up, and we get these interglacials. They are the upper peaks here, are the interglacials. And most of them are very, very sharp, actually. I mean, the temperature goes up and it comes straight back down again after, just a couple of thousand years, and the temperature is coming back down again. We're a bit different in the Holocene over on the right-hand side here, because the Holocene was an obliquity-induced interglacial, and so it lasts a bit longer. The same as it does 400,000 years ago. If you look at 400,000 years, that was mainly an obliquity-induced interglacial, and so that one lasted longer as well. But the argument from this is that, quite obviously, CO2 is the feedback agent which is controlling temperature. But there are some problems with that, and these are the problems that started me off on this quest. The first problem, of course, is that correlation does not imply causation. So we need a rationale, we need some proof, we need some evidence that CO2 is actually causal in this temperature plot. and not just following temperature. The second problem is quite a fundamental one, actually. You see the interglacials with the high peaks here. So when CO2 is high, the world cools. When CO2 is low, the world warms. So high CO2 causes cooling, according to this graph. Low CO2 causes warming, which is the complete opposite, of course, of what we're being told today. And it rather suggests, at the very least, that CO2 is a very weak feedback agent, or maybe not the primary feedback agent, and there is something else working behind the scenes to modulate the ice age cycle. And problem 3, so that's 2 problems. Problem 3 with this graph is that quite often CO2 is lagging temperature. And normally they say this is about 700 years. And so CO2 is not initiating, as a feedback agent, is not initiating warming. That is initiated by orbital cycles, which we'll talk about in a minute. And then the warming from the orbital cycles triggers a release of CO2, presumably from the oceans, because of oceanic solubility. And therefore, the CO2 can rise, and therefore the CO2 can act as a feedback agent. But if orbital cycles can raise the temperature, then why invoke CO2 at all as a feedback agent? We don't need a feedback agent. Orbital cycles can do it on their own. But of course, they can't do it on their own, as we will see in the next graph. There is a problem with this. So this is the next graph, which is CO2 versus Milankovitch insolation, which sounds complicated, but it's not very complicated. It's just orbital cycles. So what have we got in this plot? We've got the red plot is temperature again on the left, same temperatures as before on the left. Time period at the bottom, we've got today's date on the right side, going back 450,000 years this time. So we've only got 5 interglacials in this plot. And then on the right side and the blue plot, we've got insolation, the amount of sunlight energy coming down in the northern latitudes at high latitudes. And this is known as Milankovitch insolation. It's caused by orbital cycles. So Milankovitch insolation is a combination of precession, obliquity, and eccentricity. And if you mix those 3 orbital cycles together, you get this effect on Earth, which is known as Milankovitch insolation, which is a nice 22,000-year cycle, mainly predominated by precession, not obliquity. So this is mainly precession. And this has been calculated by Pierre Lascar in Paris back 25 million years. So we're pretty certain about this particular cycle. And I tend to call this the Great Year. And I think it's useful to think of it in those terms because it operates like a normal year. So a normal year, we get summers, and when we have summer in the north, we have winter in the south. And when they have summer in the south, we have winter in the north. Well, these great years operate in the same fashion. So we get these peaks in the blue plot, and they are great summers in the northern hemisphere. And while we're having a 10,000 year, as it were, great summer in the north, they're having a great winter in the south and vice versa. So the great year operates a little like the normal year, except it's 22,000 years long, roughly. It does change from cycle to cycle. And the obvious implication from this is that the great summers in the northern hemisphere trigger interglacials. And you can see those marked here on this graph. So the orange circles are high insolation from a great summer, a Milankovitch maximum, you might call it, which triggers an interglacial. You can see that in the red plot. So you get warming. And so that is demonstrating, and I think it's correct, that the orbital cycles, the great summers, trigger interglacials. And that gives us problem 4. We get so many problems from the standard interpretation because all of these peaks we see here with interglacials, they're all northern hemisphere great summers. And that's a problem for the CO2 theory because CO2 is a global gas. You would have thought as a global feedback agent that some of these interglacials would be caused by great summers in the southern hemisphere. So we would expect that maybe 2 or 3 of these interglacials would be during a southern great summer, which would be, I don't know if you can see my cursor here, but down the bottom here, at the bottom of the blue plots, where you have a great winter in the north, you get a great summer in the south. And so some of these interglacials should be caused by southern hemisphere great summers, and they are not. All of these interglacials are all northern hemisphere events, and that's a problem because now we have a regional feedback. So CO2 is not regional, it's omnipresent. Now we're looking for a feedback agent that is regional to the northern hemisphere. Yeah, that's a problem. That gives us a difficulty. But there's a further difficulty because although this is the same diagram, just with different markings on it, although great summers, Milankovitch maximum, are obviously involved in interglacial warming, not every maximum, not every great summer causes an interglacial. And I've marked them here with the purple circles, all of the maximums in insolation in the northern hemisphere, which do not produce an interglacial. Now, some of them produce a small rise in temperature. If you look at 80,000 years ago, you'll see a little bump in temperature. Maybe if you look at 220,000 years ago, again, we get a small bump in the temperature. So you might call these failed interglacials. They never actually got going enough to be an interglacial. But others, like if you look at 170,000 years ago, no response whatsoever. Same 150,000 years ago, no response whatsoever. 100,000 years ago, no response whatsoever. And this is a problem because now we have forcing. The forcing is the orbital cycles, the Milankovitch insolation. We need, quite obviously, a feedback agent because not every orbital cycle causes warming. So we need a feedback agent. But this feedback agent has to be selective. How do you get a selective feedback agent, an intermittent feedback agent? Sometimes it operates, sometimes it doesn't. Sometimes it only operates a little bit. That is not CO2 doing that. CO2 is a global gas. It should operate all the time in very much the same fashion. So we're looking for a different type of feedback agent here, which is regional, northern hemisphere, and intermittent. A tall order, I think you probably agree. Some people, because of all of these problems, have suggested that the forcing agent is not Milankovitch insolation, it's actually obliquity. So this is a plot of temperature versus obliquity. So temperature in red, same as it was before on the left-hand part of the graph. Dates are on the bottom, going back 400,000 years this time, with, again, 5 interglacials there. And the blue plot this time is obliquity, which is the tilt angle of the Earth. So precession is the wobble of the Earth, obliquity is the tilt angle. And the tilt angle of the Earth changes by 2.5 degrees. It's quite a lot, actually. Sometimes it's leaning further over and sometimes it's more upright, as it were. That is the obliquity cycle. And it's a 40,000 year cycle. So precession, 22,000 year cycle. Roughly, it does change a little bit. Obliquity, 40,000 year cycle. And again, Professor Lascar over in Paris has calculated obliquity back 25 million years. So we're pretty certain about this cycle. And in terms of their effects, well, the easy way to think about it, precession will steal, as it were, energy from the southern hemisphere and give it to the northern hemisphere during a great summer in the north. And vice versa. When you get a great summer in the south, it steals energy from the northern hemisphere and gives it to the southern hemisphere. That is precession. Obliquity is different. What it does is it steals energy from the tropics and gives it to the high latitudes. And that's why we get this change in warming, because of obliquity. But in general, obliquity is much weaker than precession. Only about 20% quite often. Depending on the strength of precession, it's normally only about 20% of Milankovitch insolation is caused by obliquity. But it's been claimed that obliquity can cause interglacials. And you'll see here marked in orange, we have 1, 2, 3, maybe 4 obliquity maxima that seem to be correlated with interglacials. And so, well, yes, it's possible that obliquity is involved, but then obliquity is a part of Milankovitch insolation anyway. It's a part of that calculation. And the other problem with this theory, of course, is that if we look on the next graph, this is the same graph, but highlighted here in purple are all of the obliquity maxima that did not create an interglacial. And some of them had no effect whatsoever on temperature. And that's a problem again, because even if you like obliquity as a forcing agent, which some people like Ubers have written about quite extensively in their papers, is being selective again. So we need a feedback agent that is selective. It operates sometimes and not others. That doesn't describe CO2. So where are we going with this? What is our hypothetical new feedback agent? I think it is this. Dust. Not so much dust in the atmosphere, which the IPCC likes to calculate a lot of. Of course, they like dust in the atmosphere. We're talking here about dust when it settles on the ground. So this is a big dust storm. I think this is somewhere in America, actually. I don't know where this is. And dust can have a big effect on climate, especially when it lands on the ice sheets. So what we're looking at here is the Arctic, and it's being deposited with lots of dust. This is from the Dark Ice project, which was running about 10 years ago, I think it was now. And they were looking at the effects of industrial soot landing on ice sheets in the north. And they recorded a number of ice sheets that were covered in, I think what they said this was industrial dust from the industrialization of China over the last 2 decades. This is Chinese industrial soot on the high latitudes. And of course, this will affect the albedo, the reflectivity of the ice. Obviously, it's darker. We can see it's darker. And the darker the ice, the more insolation it can absorb, the more sunlight it can absorb. And if it's absorbing more energy, then it can melt, it can ablate, and you can melt your ice sheets. But the poor old Dark Ice project only got 1 year of funding, and then their funding was cut. And so they have no longer operated. So we don't have enough data on this as we would like. So that is the effect of the effect of dust on ice sheets. And so does this apply in any fashion to the ice ages? Well, yes, it does. And this has not been highlighted very much, actually. You know, I've read a lot of papers on the ice ages, and dust does not appear in very many of them. There's 1 or 2, Mauld and Janopolsky, but I think their ideas are incorrect, as we will see in a minute. So there is dust during the ice ages. And here is a plot of temperature and dust. So on the top, we have in red, we have temperature again, going back from 0 to 800,000 years ago. So we've got all of the ice ages here, all of the ice ages beyond the MPT. The mid-Pleistocene transition is when ice ages changed into their familiar form that we're familiar with now, the big ice ages. Before that, the ice ages were very small and spaced about 40,000 years apart. So yes, temperature on the top, same as we've seen before. Dust on the bottom in green. And this is from the Epica ice core down in Antarctica. Now, you can't do this with Greenland data because Greenland only has a record going back 120,000 years. It only has the last ice age, basically. So if you want a better record of what's been going on for the last nearly million years, you need to go down to Antarctica. And so this is data from the Epica ice core. And from that, we can gather all of this data. So you can check, and very diligently, they have checked through the ice core for the oxygen isotope ratios, from which we get temperature, which is where we get the red plot from. And then in the same ice cores, we can find layers of dust. And so they can be measured as well. And now we get a record of the amount of dust in the ice core. And it obviously changes. We have peaks here in the dust record. And what I've done on this chart is I've grayed out any areas with high dust. So where you see a gray band, a gray column, that means high dust. And you can see it correlates with high dust down the bottom. So wherever we get a gray band, high dust, it comes just before an interglacial. So every single interglacial is preceded by high dust, which is interesting because if dust was the feedback agent and dust was getting onto the ice sheets, this would explain many of the anomalies that we find in the CO2 type record of ice ages, the CO2 explanation, I should say, of ice ages. So it explains the intermittency. Well, we can see why it is intermittent because we only get dust just before an ice age. Typically, it's about 20,000 years, 10,000 years just before an ice age. We get a whole 10,000 years or more of dust. Before that, there is no dust. So if we're looking at great summers, Milankovitch maxima, if there's no dust, then the ice sheets will be pristine white. And of course, they can reflect away all of that increased energy from the sun, and there will be no effect on temperature. There will be no melting of the ice. And that can explain the missing ice ages. Within the precessional cycle, the Milankovitch cycle, any maximum that comes before a period of dust will not have any effect on the ice sheets at all because the ice is pure white and very reflective. It can only have an effect when there is dust on the ice sheets, and now the insolation, the energy from the sun can get a grip on those ice sheets, be absorbed by that dark ice and melt and ablate the ice. So that explains the intermittency problem. It also explains the Northern Hemisphere problem because CO2 is a global gas. As we said before, we should get ice, we should get interglacials on northern and southern insolation maxima, great summers in north and south. But we don't. We only get them in northern great summers. But of course, with dust, that's exactly what we would expect because all of the major land masses are in the north. Therefore, all of the major ice sheets are in the north. And all the dust is being produced in the Northern Hemisphere as well, because it's coming from the Gobi Plateau, as we will see shortly. So papers like we had from Ganopolsky are wrong. Ganopolsky was saying that because it's been recognized that there is dust within the ice record, that this is glaciogenic dust. It's been caused by the ice sheets grinding up dust in front of them and that dust going back and falling on the ice sheets. Well, that's wrong in several respects because this dust on the ice sheets, this is as measured in Greenland, has been isotopically analyzed and demonstrated to come from the Gobi Plateau, not from glaciogenic dust. And that's important because the Gobi dust is intermittent, as we will show in a minute, whereas glaciogenic dust will be being produced all the time. So why do we get this intermittency in dust? Why do we only get it just before each of the ice ages? Sorry, just before each of the interglacial. Well, it's been said that dust production, this is the same graph we've seen at the very beginning of this talk, that dust production was produced because during an ice age at the glacial maximum, it's very cold and it's very dry. And therefore, a dry atmosphere will not have very much precipitation, and therefore you might get desert formation, and therefore you might get dust. But nobody has really correlated that dust with the melting of the ice sheets for some reason, but it's pretty obvious that that can be used as a feedback agent if that dust gets on the ice sheets. But I think they're wrong. It has nothing to do with precipitation or the humidity of the atmosphere during the LGM. Because, well, no, we'll come to that in a minute. There was actually quite a lot of moisture around during the LGM. So what I think is happening instead is we have a lack of CO2. So you can see that from this graph. When we go down to the glacial maximum, CO2 drops to a minimum. It comes all the way down to 180 parts per million. Due to oceanic solubility. The colder the seas are, the more CO2 they can absorb out of the atmosphere. And so CO2 in the atmosphere drops. And so we get a minimum of CO2 at the glacial maximum. And CO2, of course, is plant food. And on this picture, we can see plants that have been grown in different concentrations of CO2. So on the right, we have 800 parts per million, going down on the left all the way down to 30 parts per million, which is really low. And we can see that plants do better when there is more CO2, because CO2 is plant food. CO2 is the most important gas in the atmosphere. Without CO2, all life on Earth will die, except for fungi. But even they will run out of food eventually, and they will die as well. So the whole of the biosphere is dependent on CO2. And the more we have, the better. Now, the different types of plants here, we've got C3 plants on the top and C4 plants on the bottom. Now, C4 plants are rather different. They use CO2 in a different fashion. And they don't need quite so much of it, which is why you see, although the plants are getting smaller, they do not die. Now, C4 plants are the fleshy plants. So these will be things like maize or sweet corn. No, not sweet corn, sugarcane. They are C4 plants. But if you're going up into the high altitudes, like going up on the Gobi plateau, which we will in a minute, you will not find C4 plants up there because C4 plants don't like cold conditions. So we're talking about C3 plants, which are pretty much all of the grasses, all of the trees. Most of the plants we find, I think it's something like 90% or something of that nature, 85, 90% of plants are C3 type plants. And as you can see, they really begin to suffer when CO2 gets low. So on the right, we have 800 parts per million, and the plants are growing well. 400 parts per million, that's the current concentration we have. And the plants are growing, well, not quite so strongly, but they're still growing well. If we go back to pre-industrial levels, that's 280 parts per million. That's about here. The plants are a little bit smaller, but they can still grow. If we go back to the glacial maximum, we come down to 180 parts per million. And plants are beginning to suffer a little bit at that sort of concentration. And it's recognized that if you come down to 150 parts per million, then the plants cannot complete a life cycle. So although they're on this diagram, they are still alive, they don't have sufficient energy to complete a life cycle, so they cannot breed, they cannot produce seeds, and therefore within a generation or so, those plants will be dead. And the thing is that if you get large areas of dead plants, then we can get what is known as CO2 deserts. Something that is not talked about very often. We all understand what a precipitation desert is, but you can get a desert from a lack of CO2 just as much as you can from a lack of rain. And if you don't have enough CO2, you will get CO2 deserts. And therefore, if we plot dust against CO2, we will see a correlation. So here is a scatter plot of dust on the left side. This is from Greenland data, going from very little dust at the bottom to 1,000 micrograms per gram of ice, the top there. And along the bottom, we've got CO2 in parts per million, going from the pre-industrial, 280 parts per million, going all the way down to 180, which is the minimum that we had pretty much during the glacial maximum, the LGM as it's known. And this gives you a very nice scatter plot, which gives you a fairly straight and constant line there. There is a correlation between CO2 and dust production. And the question obviously has to become, is that causational? Is CO2 causing dust? And I think it is, and we'll have a look at that in just a minute. So there is a relationship between CO2 and dust, but where was this dust being produced? Well, we've talked about this a little bit already. It was being produced up in the high Gobi plateau, just in northern China, as it were. And this is a high plateau region that currently is mostly steppe grassland. So it's like a prairie, I suppose. So most of it is not desert, apart from the Taklaman over on the west side here. Most of this is not desert. It is a steppe grassland. But during the glacial maximum, of course, it might have been 180 parts per million CO2 at sea level. But up on the high Gobi Plateau, this goes up to 2,000 meters, 2,500 meters, some of this, we're a lot higher. And the air is a lot thinner. And so there will be less CO2 for the plants to actually enjoy as their food. And if we get below 150 parts per million equivalent, obviously the amount of CO2, the proportion of CO2 doesn't change. But because the air is thinner, the proportion of CO2 can come down to 150 parts per million equivalent at high altitude. And so at high altitude, you can run out of CO2, you can get CO2 deserts, and the whole of this area became a CO2 desert. And we know this because the dust in Greenland has been identified as coming from the Gobi Desert by isotopic analysis. And also, if you look at the lowest plateau, which is on the eastern part of China, just down the road, as it were, from the Gobi Desert, the whole of the lowest plateau is formed from dust from the Gobi. And that dust, we've got 1 million years of a dust record in the lowest plateau, equates to the same strata as we get in the ice cores from Greenland. So all of the ice eras and the interglacials are present there in the strata of the lowest plateau. So we know that the Gobi Desert was producing copious amounts of dust during the ice ages because we have the record of it. And of course, if that dust gets on the ice sheets, it can darken them, it can reduce their albedo, and that can cause ice sheet warming. And we can get a good idea that this is causal, that it's not just coincidental, from this graph. Now, this is an interesting graph. This is a graph of modeled dust against land area. So along the bottom, we have CO2 going from 300 to 180. That's from pre-industrial CO2 down to glacial maximum CO2. On the left side here, we have the modeled dust. This is pretty much the same as we saw in the scatter plot just a moment ago. The amount of dust that's coming out of the Gobi Plateau, and obviously the amount of dust increases as CO2 decreases. And then the blue plot going alongside it is the modeled land area below a certain altitude. And the altitude we've chosen is 150 parts per million equivalent of CO2. So obviously, if you have CO2 at the surface, say, of 240 parts per million, at some point, as you go up a mountain, you will find that the CO2 equivalent has dropped to 150 parts per million equivalent, a partial pressure of 150 parts per million of CO2. And that you could term as being the death zone. Anything above that zone will be the death zone for plants because they cannot grow in levels below 150 parts per million equivalent. And now that will start at the top of mountains. So initially, the death zone, like we get with mountains at present with temperature, there will be a death zone above which trees cannot grow because of the temperature. Well, during the ice ages, we had a death zone caused by CO2. And as that death zone comes down the mountainside, so the land area increases and increases as we come down into the valleys and then down onto the lower plains. And the land area above the death zone increases exponentially. And that's what we've plotted in the blue plot here. And as you can see, there is a good correlation here between the amount of dust and the land area available above the CO2 death zone. And that again is causal. It's the lack of CO2 that is causing the dust, and that amount of dust will increase exponentially as the death zone comes down the mountainsides and into the valleys. And so we can we can plot dust against CO2 again in a different fashion, which shows us the good correlation we get between dust and CO2. So at the beginning of this talk, we saw the good correlation between temperature and CO2, which is a correlation. It's not causal, but it's a correlation. Here we see a good correlation between CO2 and dust, and this is causal. So along the bottom here, we're going back to our old favorite of 800,000 years. So the full ice age cycle after the MPT. And so we've got 10 interglacials there. And on the left, we have CO2 in parts per million, at sea level parts per million, of course. And that is in blue. So that's the blue plot going up and down. And on the right side, we have dust, which is the green plot. Now, the dust plot is inverted and exponential, just to reduce the peaks. So the dust plot is upside down, so it can correlate well with the CO2 plot. And as you can see, when CO2 is high, dust is low. When CO2 is low, dust is high. And this is why we get this dust production just before every interglacial. It's because of a lack of CO2 causing CO2 deserts, which causes dust, which allows that dust to settle on the northern ice sheet. We can have a table of the effect that will have on the ice sheets. So this is a quick table of the expected changes that this dust will have when it falls on ice sheets. So this is looking at albedo changes on the ice sheets. So normal ice, fresh ice, will have an albedo of 0.9. So albedo goes from 1, which is pure white, down to 0, which is pure black. And fresh ice and snow will have an albedo of 0.9. Now, if we can reduce that albedo just down to 0.6, and it could go a lot less than that if you get a lot of dust on it, then the increase in energy absorption by the ice during a great summer in the northern hemisphere is 135 watts per square meter. That's quite a lot. And if we can get that albedo down to 0.5, then the increase in absorption is 180 watts per square meter. An enormous amount, because if we're talking about CO2, of course, you'll probably remember that when they're talking about CO2, they're talking about an increase in feedback from CO2 of 3 or 4 watts per square meter during the entire interglacial period, which is 5,000 years. But it's not really the entire ice age that we're worried about. To go from one decade to the next decade or one century to the next century, we need some warming to increase the temperature in the climate, to increase the temperature of the seas, to allow more CO2 to come out of the oceans. And therefore, we get an increase in CO2, which will then feed back to give us a CO2 feedback to warm the interglacial. But the warming effect we get per decade for CO2 is 0.008 watts per square meter, virtually nothing. Whereas here, with ice sheet albedo, we're getting 180 watts per square meter, not just at the end of that decade, but every day, every decade, every century, every millennium, all the time during the interglacial warming period. So instead of getting 0.008 watts per square meter measured globally, we're getting 180 watts per square meter when measured regionally in the high latitudes on the ice sheets itself. And of course, that is where we want to measure the insulation absorption. Because if you think about it with snow and ice in an annual winter, that snow and ice in Canada is depleted, it's melted and ablated by the sun in the Northern Hemisphere, in Canada itself. It's not worried about the temperature down in Argentina. So the global effect of CO2 is largely irrelevant. What we're interested in is the solar absorption on the ice sheets themselves during the northern Great Summer. And that is provided by dusty ice albedo. And that is what can melt and ablate the ice ages in a very short space of time. Remember, these ice sheets have built up over maybe 100,000 years. And then the forcing and feedback agent can destroy those ice sheets within 5,000 years. It's a very, very strong warming that will get rid of these ice sheets. And CO2 cannot provide that strong warming. And we can still see that dust on the ice today. So this is from Greenland. And what we're seeing here is dust from the last glacial maximum. So let's annotate that a little bit so we know what we're talking about here. So this dust, this dark area on the right, is dust that fell on the northern ice sheets just before the last interglacial, before the Holocene interglacial. So this is dust from, say, 25,000 years ago up to about 12,000 years ago. That's when the dust fell, and it was that dust that caused the melting of these ice sheets. Then we see it stops, and we get a white band before going back to another darker band. And that white band is the initial warming of the last interglacial. So this is the Bolling Aneroid warming, which you will see on any graph, was the initial warming after the last ice age. And then, of course, we get another band here because this is the Younger Dryas. After the Bolling Aneroid, the world was plunged back into another mini ice age, which is known as the Younger Dryas, which was a 1,000 years of cold weather again, cold climate. And that produced another layer of dust because the world cooled, the oceans cooled, the oceans absorbed more CO2, there was less CO2 in the atmosphere. That causes more CO2 deserts and we get more dust, and that's why we get another dust ring here. So this second dust ring is further proof that we actually did have the Younger Dryas cool period between about 12,000 and 11,000 years ago. And then all of the dust disappears because now we're in the Holocene, the warm period of the Holocene. Now, that is how dark this ice can get, but originally it would have been much darker than this because this ice has been squeezed out of the bottom of the Greenland ice sheet, rather like toothpaste out of a tube. It's been forced out of the bottom of the ice sheet and it's thin and therefore not as concentrated as it used to be. Greenland is a funny island. It's without its ice. This is what it looks like underneath the ice. And it's a big dish, basically, presumably caused by the weight of the ice, just, crushing the land down below it. And so it's a dish in the center with a whole ring of mountains around the outside, which is why the Greenland ice sheet is so stable and it stays in position because it cannot slip off. And it's very difficult for the ice at the bottom because within ice sheets, a lot of the melting happens on the underneath of the ice sheet, not on the top, especially in the upper areas of the ice sheet in Greenland. That's largely irrelevant. It doesn't melt. It melts at the bottom due to the pressure of the ice above and because of some warming from below, because of the land itself being warm. And it melts underneath. And then that water and that ice has to be squeezed out from underneath over these mountain ranges, which is very difficult for Greenland. And so Greenland tends to be quite stable. But when it is squeezed out, it's thinned like toothpaste out of a tube. And that's why on these images, the dust looks, well, not as dark as it would have been back in its day during the glacial maximum. So that's pretty much nearly the end of this new discovery on Ice Age modulation. But while I was going through it, I did find what I considered to be an error in climate modeling for the paleoclimate. This is a PMIP map. This is, what do they call this? This is the Paleoclimate Modeling Intercomparison Project, or PMIP. And this is a map of glacial maximum precipitation. Obviously, they're interested in the climate as it was back in the glacial maximum era. And so they produce these maps based on, the various bits of data they get in. And this shows the red area, the red and orange areas across the tropics here have very low precipitation. You can see on the left down the bottom here, red and orange mean low precipitation. And that was one reason, of course, why they were thinking that these precipitation deserts appear during the last glacial maximum. But of course, that's contradicted by Chinese scientists in the Gobi region who have said that the Gobi was actually moister, more humid than it is today. It had more rainfall back in the glacial maximum. Why? Well, because the temperature doesn't change much. So in the tropics, the temperature does not change. It changes a great deal in the high latitudes, by 12 or 14 degrees in the high latitudes. But in the tropics, temperatures during the glacial maximum only change by 2 or 3 degrees, not very much. So perhaps you might not expect a very big change in precipitation if the temperature is not changing very much. So how do they find out this data? Well, they do it by looking at sea temperatures, and sea temperatures are determined by doing cores in the sea, bringing up the mud, and looking for the different phytoplankton and zooplankton that have been deposited in oceanic deposits. And from the different types of planktons that you find, you can determine the sea temperature. And that's why they know that the temperature in the tropics did not change much, only by 2 or 3 degrees. But to get the humidity of the air, you need temperatures at altitude as well. And how do you do that? Well, you look at trees. So what you do is you have a look at the tree line. And this is a very good tree line going up a mountain. And it's been determined by Corner et al. And various others that these tree lines are determined by temperature. Temperature in the spring determines whether a tree can grow or not grow at altitude. And so if you can go back down the mountain and you can find the ancient tree line that was there 20,000 years ago, you will know the temperature on this mountain during the last glacial maximum. And that's what they did. And it produced some odd results because it produced temperatures that were much too low. And therefore, the lapse rate between the surface and the mountain was far too high. And it is the lapse rate that determines the humidity of the atmosphere. Now, a humid atmosphere is 1.5 degrees per 1,000 foot, normally, and a dry atmosphere is 3 degrees per 1,000 foot, normally. And they were coming out with lapse rates that were even above 3 degrees per 1,000 foot. They were saying that the atmosphere is really, really dry, had a very high lapse rate in the tropics. And that's why they have, in the PMET map, these red areas along the tropics. Well, hold on a minute. I think they've forgotten about the full effects of CO2. So they've missed the importance of CO2 deserts, which we've already talked about, that the Gobi was a CO2 desert, not a precipitation desert. And they've forgotten that tree lines during the last glacial maximum were controlled by CO2, not by temperature. So we were talking about the death zone for CO2 going up a mountain before. Well, the death zone came a long way down the mountain sides during the last glacial maximum because there was not enough CO2 for the C3 trees to be growing at this altitude. And so the tree lines were determined by CO2, not by temperature. And so the temperature that they achieved for these mountain sides, we can release them from their discoveries, their research, and put them back to normal. We can put the lapse rate back to normal because these tree lines are being determined by CO2, not temperature. And therefore, we can eliminate all of these red areas in the tropics because I don't believe that the precipitation was that low. I think most probably the precipitation in the tropics during the glacial maximum was pretty much the same as it was now because temperatures there in the tropics didn't change very much. That is why the Chinese scientists are finding the Gobi Plateau was relatively moist during the glacial maximum. So I think this map is in error. And it needs a rethink on this map because I think this is wrong. So that pretty much is the theory of ice age modulation. And this is a good theory, I think, because it encompasses all of the many factors you can see on this best diagram that actually are involved with the climate during ice ages. So let's have a quick summary of what's going on here in this diagram. So glacial periods are forced by orbital cycles, mainly by precession, which we've already seen. But the glacial cycle needs a feedback mechanism. We've seen that because many orbital cycles have no effect on climate whatsoever. So it needs a feedback mechanism. The glacial period with ice on the ground is maintained by high albedo of these high albedo ice sheets in the northern hemisphere, which can reflect all of this energy from the sun back into space. And that has, I suppose, I've not actually calculated the actual data, but that has the potential to continue ad infinitum until you end up with a snowball Earth, basically. There's nothing really to stop that increased icing of the world just creeping further and further south all the time with this high albedo ice reflecting all of the sunlight back into space until you get a snowball Earth, basically. But we do have a system of getting out of this runaway cooling because colder temperatures, which we get especially in the north, means less CO2 because of ocean solubility. The colder the seas, the more CO2 they can absorb. And so we get less CO2 in the atmosphere. Less CO2 in the atmosphere means more CO2 deserts, especially on the Gobi Plateau, and therefore more dust. More dust means lower albedo on the northern ice sheets, and we've seen that dust in the ice sheets themselves. And that lower albedo means more insolation absorption from the sun. And the system there, this is what's good about this system, is this feedback agent precedes the interglacial. Unlike CO2, where it seems to follow the interglacial, which is sort of not possible, feedback agents are supposed to precede, not follow. So the system just sits and waits. It's primed and ready, and it's waiting for the next great summer Milankovitch maximum in the northern hemisphere. It's got all of the ice. It's got 20,000 years of ice, maybe 15 or 20,000 years of dust in the ice. So the ice sheets are ready and primed for getting more insolation from a great summer in the northern hemisphere. And as soon as that great summer arrives, we get more insolation, we get more energy from the sun, and now the ice sheets can melt because they have a very low albedo. And that is what melts the ice sheets and melts those ice sheets in 5,000 years. So we get 100,000 years, as I said, of the buildup of this ice, and then it all melts in 5,000 years. And so the conclusion from this is that it is low CO2 that causes warming by causing CO2 deserts. It's low CO2 causes warming during the ice ages. And note also, when we get to the top of an interglacial, high CO2 cannot resist orbital cooling, again suggesting that CO2 is a very, very weak feedback agent. So every time we get to an interglacial where CO2 is at a maximum, we don't get runaway warming, we get cooling. As soon as the orbital cycles go into cooling mode, we get cooling. CO2 cannot resist it. So CO2 is a very, very weak feedback agent. The primary feedback agent during interglacials and all of the ice ages is dust albedo, the reflectivity of the ice. And as an aside, if we look into the future, we are standing on the cusp of a new ice age. Only about between 1,000 and 2,000 years from now, we go back into the orbital conditions, which will precipitate a new ice age. But there's only one caveat with that, and it's not CO2, because CO2 is weak, as we've seen, and that's not going to stop an ice age. It never has, and it never will, so it's not going to stop this one. The only caveat is that because of low eccentricity, we have a very low eccentricity period. The eccentricity cycle is 400,000 years, and we're at the low point in eccentricity. Low eccentricity means precession is weak. Obliquity remains the same, but remember, obliquity is the weak partner in this union. The strong partner is precession, but precession is weak at present because of low eccentricity. So looking into the future for the next 50 to 100,000 years, we have very weak great summers and very weak great winters. So it's not at all certain that there will be enough cooling during the next great winter, which, as I say, starts in about 1,000 or 2,000 years' time, that there will not be enough cooling to force an ice age. But even if there was, now, because of this research, we know how to oppose it. We can actually influence the climate. We can stop the ice ages. And it's very simple. All you do is you go up with large aircraft and you coat the northern ice sheets with carbon dust. And that will promote melting, and it'll stop the ice sheets from increasing. And so in that case, carbon will cause warming, but not carbon as they like to mention so often nowadays, where they're meaning carbon dioxide. This is real carbon, it's soot. If you coat the ice sheets with soot, you will stop them, you will stop them advancing towards the south. It will simply melt them because of the increased absorption of sunlight. Just as northeast Siberia escaped the ice ages. Now, there's a conundrum for you. The ice sheets covered all of the northern hemisphere, of course, during the ice age, except for northeast Siberia, which never had an ice sheet. Why did that escape? Well, because it had sufficient dust coming off the Gobi Plateau all the time that coated it in dust, and it prevented the advancement of the northeastern Siberian ice sheet. It never advanced. And so we are pretty sure that dust is the key to ice ages. And the key to dust is low CO2 and CO2 deserts. So that is the new theory for ice age modulation. And I have to say that I think it explains every facet of the ice age cycle, which the CO2 feedback explanation never did. There were far too many holes in it. 5 of those holes we've looked at already in this talk. So this is the new theory for ice age modulation, and it's been out there for 5-6 years now. And nobody has really made a valid criticism of this theory. Nobody has shown any error in its logic or its calculations. And so I do think this is how ice ages are modulated. And I think that's a fairly important discovery. Just to show the people the paper again, Modulation of Ice Ages via Precession and Dust Albedo FIDEX by myself, Ralph Ellis, and Professor Michael Palmer. Finished, it was published in 2016. So as I say, it's been out for a while now. And it's an all-encompassing paper. It tells you all you need to know about the Ice Age cycle.
Have you had any feedback from Richard Lindzen or other luminaries in the climate field about this, either way, about what they think about it?
I've had feedback from them, but in a very minor manner. So they've acknowledged the paper and they've said, yes, they like it, but they've not really engaged much with the information that's there. So I've not had any discussion with them, although I've put this paper obviously out to everyone who's involved in paleoclimatology. I've not really had any discussion with it in the field, as it were.
Okay. Our next question is, where do you think Earth's temperature is going from here in the more short term, like by 2050 or by 2100? Do you have any thoughts as to what might be coming up in that time frame?
Well, this was a part of a paper that I was going to make with Donald Rapp and various other professors, because I had some good responses from Donald Rapp and a few others, Spencer, before he passed away. And we were going to make a new paper on the more immediate effects of dust on the ice sheets, looking at the possibility that modern warming can be influenced by Chinese industrial dust on the ice sheets. So looking at the short-term albedo effects of industrial dust. That project failed. That ended when he passed away. And we've not been able to pursue that any further. But it would be interesting to look at that and also look at the potential for the next ice age coming in the next 1,000 years or so. I did some preliminary work on that, and it looks like we have the right conditions just about, only just, within the next, as I say, 1,000 or 2,000 years' time. But it's a very, very mild great winter that's coming. So if we'd had a standard great winter, you could say immediately that at this point we enter into cooling conditions. But on this occasion, as soon as we enter into cooling conditions, the conditions start to reverse and coat back up into warming again. So it's not entirely certain that we'll ever get another ice age for the next few thousand years.
Okay. Do you think the medieval warm period was global, or was it warm in the north and cold in the south, or what do you think?
Don't know on that. We've been mainly looking at the ice ages, of course, not the recent climate. And nobody really knows why the warm period and the little ice ages happened. Clearly, there is modulation within the Holocene. So the Holocene started from roughly about 12,000 years ago. The peak of the Holocene warming was about 8,000 years ago. That was known as the Holocene maximum. That's when the Sahara Desert turned green and fertile. But that was not necessarily caused by warming. You see, there are so many factors involved in the climate that it can be very confusing. A lot of people have said, look, warming during the Holocene maximum turned the Sahara green and fertile. Yes, but that might not have been the warming. That might be because the Holocene is a obliquity modulated interglacial. So it's mainly controlled by obliquity because precession is very weak at present. And with obliquity, of course, the Earth is actually changing its angle of tilt. And so the ITCZ, the intertropical convergence zone, may well move with that change in obliquity. And therefore, it may move up sufficiently that the Sahara Desert is now underneath, separated from the within the range of the ITCZ. So it gets the thunderstorms coming off the ITCZ. So it might be a change in the weather patterns and bands around the Earth caused by obliquity and not simply by the warming. But the other peaks, because if you look at the temperature over the Holocene, it's full of little peaks, which some people have managed to derive periodicity from that. And I think someone was saying there's a 400-year periodicity, and there are other shorter ones like an 80-year periodicity. But the explanation for those changes is totally uncertain. We don't know why we have these small deviations in temperature during the Holocene period. Could be solar influences, but I've seen work done on the sunspot cycle, and this is mainly by people like Eschenbach and so on, who cannot find a sunspot signal within the climate record. So the sunspot cycle is normally about 11 years, between sort of 10 and I suppose 14 maximum. That cycle doesn't appear to be present within the climate record that we have. But when we go back to things like the Little Ice Age and the medieval warming period, we don't have enough information. We don't have enough cycles to say what is actually forcing that. Was it a grand minima in the lack of sunspots during the 18th century, 17th century? It's possible, but we've only had one cycle. So it's impossible to say from one cycle if that was a causative effect that was controlling temperature. We simply don't know.
Very good. My last real question is there a CO2 death zone for plants currently on mountains, or how high up do you have to go to get to that 150 parts per million equivalent?
No, we've gone up so high now that no mountains are affected by the death zone. So this only occurs during ice ages when we get below, say, 250 parts per million. Once we get below that stage, we start getting into the death zone at the very, very top of mountains. And then that death zone, as I said, goes down the mountainside, the lower the CO2 at sea level, until it becomes dominant, more dominant than temperature or precipitation. And that has not really been investigated or studied really within standard paleoclimatology. I've not seen any papers that calculate that. And I read so many papers on this topic before writing mine. I have to compliment Professor Palmer on this because he was my mentor on how to write this paper. And the first thing he did is he threw something like 70 climate papers at me and said, read all of those papers and then come back to me. So I had to plow through all of this data, looking at what has been produced on the climate record over the last few decades within science papers. And I didn't see any mention of CO2 as a causative agent that is causing deserts, that is causing death zones on mountainsides. I just did not see it at all. So if someone knows of any old papers that are mentioning that, please do get in touch. I would be very interested, but I've not seen any papers that mention it.
And this is the first I've heard of it. Very interesting stuff. And my last question here is, could I put your slides up on my Substack, or are they available someplace for people to look at if they want to go back?
That's sure. Yes, I will pass them across to you. So I'll send a whole list of the diagrams, and you can put them up. No problem at all.
Okay, I'm all set. So thank you very much. I really appreciate you doing this. I think people are going to enjoy watching this, and maybe if you have more time, you can do another one. Yeah,
sure. Glad to be on the show, and I hope people find it informative. I'm always open to questions, so if people have questions, this will obviously be up on various video platforms. I'm more than happy to answer questions and engage in discussions. That's the whole point of this. We need to discuss these topics, not shut down conversation of these topics just because I'm not mentioning CO2 in the approved fashion. So yeah, let's have a discussion about this.
I'll let you go, but thanks again. I'll talk to you next time.
Thank you.
All right. Goodbye.